Welcome to the 6th video session from the broad area of study fluid kinematics. In this lecture we continue to do numericals belonging to the section stream function and velocity potential function. So these problems are typical ones which were asked for the previous university examinations. So we start with a very simple problem. A conical pipe diverges uniformly from 100 mm to 200 mm diameter over a length of 1 meter. Determine the velocity of flow at the midsection if the rate of flow is 0.2 cubic meter per second and is constant. It's a very simple problem. What is given here? You have a gradually diverging pipe, and so this is the representation of this gradually diverging pipe. So it is diverging from D1 diameter 100 mm at inlet, and at the outlet the diameter is double, that is 200 mm, that is D2. So what is it? Is uniform divergence. So what is the diameter at the midsection? Length is 1 meter. So at the middle, what will be the diameter? It is the half of the sum of the diameters of the inlet and outlet sections. So that is 100 plus 200 divided by 2, that is 150 mm. So at the midsection, the diameter is 150 since the conical pipe diverges uniformly from inlet to outlet. So we need to find out the velocity at the midsection where the diameter is 150 mm. So for this, the rate of flow, which is also called a discharge, which is generally designated using the symbol, using the letter capital Q. Okay, so that is discharge Q as per continuity equation is a constant. So discharge is constant, it is given here also. So Q equal to area into velocity, that is the equation that is known to us. Q for a pipe or a gradually increasing area pipe or any section, how can we find out the discharge? Q is equal to area into velocity. Okay, so cross sectional area into velocity. So Q is 0.12 cubic meter per second, that is 0.12 meter cube per second, that is equal to the area at the midsection into velocity at the midsection. How to get the cross sectional area of a circle? The cross section is circular, so pi by 4 into d square. Here d is 150 mm or 0.15 meters. So pi by 4 d square into velocity at the midsection. So velocity at the midsection you can calculate as 0.12 divided by pi by 4, 0.15 the whole square. So it is 6.82 meter per second. So it's a continuous flow that is happening. So discharge is always area into flow velocity. That is a basic equation which can be used for estimating velocity at any interval, at any section, provided the discharge remains the same. So also when the area increases, from the equation Q equal to area into velocity, if the discharge is constant, if the area increases, definitely velocity reduces. So that is what happening in a diffuser. So what is happening in a nozzle? In a nozzle is having a gradually decreasing diameter tube, section. So as the diameter is decreasing or the cross sectional area is decreasing, the velocity should increase. Okay, now we'll move on to another problem. So that is regarding stream function. Already we had done 2 problems from the section stream function. We are continuing our discussion on stream function. We will do some more problems also. If stream function of a flow field is given as psi equal to 3xy, okay, find the velocity components at point 13 and at point 33. determine the discharge between the streamlines passing through these points. So the stream function is given as psi equal to 3xy. We know how to get the velocity components if stream function is given. It is a derivative. Okay, so you can get the velocity components u and v by differentiating psi with respect to x as well as with respect to y. So in that equation you are getting for u and v, if you substitute the corresponding data points, x coordinate 1, y coordinate 3, here x coordinate 3, y coordinate 3, you will be getting u and v, which are the velocity components at these 2 points, point 13 and point 33. Okay, then how to get the discharge between the streamlines? While describing the characteristics of the streamlines, we had discussed that there is no cross flow in a streamline system because velocity of any point on a streamline is along the tangent to the streamline at that point. So there is no flow across the streamlines. That means what? And also we had discussed a stream tube. Since there is no lateral flow, a set of streamlines can be approximated as a stream tube with fluid entering at one tube and the fluid leaving at the other end. Fluid entering at one end and leaving at the other end of the stream tube. So the difference between the stream functions of the two streamlines will give the discharge or the rate of flow between the two streamlines. Okay, we'll describe more on this. We'll try to do this problem. As I already told, psi is 3xy. As per the definition, u equal to dou psi by dou y, that is equal to 3x. The y component of velocity v equal to minus dou psi by dou x, that is minus 3y. So velocity component at point 13, you substitute x equal to 1 and y equal to 3. So it is u equal to 3 meter per second and v equal to minus 9 meter per second, and the resultant velocity is square root of u square plus v square, that is square root of 3 square plus minus 9 square, and it is getting the resultant velocity equal to 9.49 meter per second. Same procedure you adopt for the point 33, you are getting the resultant velocity as 12.73 meter per second. So the first part is over. Second part, you need to find out the discharge between the streamlines. As I already told, discharge between the streamlines by taking into account the property of a streamline is difference between the stream functions, that is psi 1 minus psi 2 in absolute unit. So at point 13, what is the equation of a stream function? Psi equal to 3xy, so x is 1 and y equal to 3. So 3 into 1 into 3, that is 9. So psi 1 we represent at point 1, or the streamline which is passing through point 1, you can represent as psi 1, and psi 2, so the coordinates should be x equal to 3, y equal to 3. So 3 into 3 into 3, so it is 27. Psi 1 is 9 and psi 2 is 27. If you take the difference of the stream function and substitute the values, you will be getting 9 minus 27. In absolute unit, it is 18. So the discharge of flow between the two stream functions, or the rate of flow of fluid between the two streamlines given, is 18 meter cube per second in absolute units. So this is very important. And now we move on to the last problem in this section. This problem consists of 5 parts. Okay, so this is a comprehensive problem that covers almost all properties of fluid flow, like velocity and acceleration, continuity equation, how to get the discharge between the streamlines, rotationality estimation, velocity potential, and satisfying the Laplace equation by the velocity function as well as stream function. So this problem is quite comprehensive in nature. This is the last problem in this section. The question goes like this: the velocity components in a two-dimensional incompressible flow, for example water, 2D flow, only x and y components are there for velocities, flow field are expressed as u equal to y cube by 3 plus 2x minus x square y, v equal to xy square minus 2y minus x cube. So it is a steady flow, two-dimensional in nature, and the velocity components u and v are given. Part A, determine the velocity and acceleration at point 1, 3. So how to get this? This is the basics. We are applying velocity u and v are given in terms of x and y. Here at this point x coordinate is 1 and y coordinate is 3. You just apply y equal to 3 and x equal to 1 in the equations for u and v. You will be getting the velocity components, and the resultant velocity component, as we have already done in many problems, it is square root of u square plus v square. That is done here. U is given, v is given. At 1, 3, u is 8 meter per second, v is 2.67 meter per second, and the resultant velocity is 8.43 meter per second. So we are quite familiar with this calculation. Second part of first question, that is acceleration. So how to get the acceleration? Eulerian acceleration. We have the summation of the respective convective component as well as temporal component. Okay, so this also we had attempted, we had done the problem. This is a convective component, this is a temporal component for ax. Similarly, this is a convective component and this is a temporal component for ay. There is no az. So only thing is you have to differentiate u with respect to x, dou u by dou x, dou u by dou y. So what is dou u by dou x? Dou by dou x of this. Okay, so it is 2 minus 2xy, that is written here. Similarly, you can calculate dou u by dou y. Dou u by dou t is 0 since there is no t present in u as well as in v. So it is a steady flow. So dou v by dou x you can calculate, dou by dou x of v, dou by dou y of v, dou v by dou y, and dou v by dou t. So if you substitute all these partial differentials in the equation for ax and ay, and at point 1, 3 you substitute x equal to 1 and y equal to 3, you will get ax equal to minus 10.64 meter per second square, ay equal to 74.68 meter per second square, and the resultant acceleration is square root of ax square plus ay square, that is equal to 75.43 meter per second square. Okay, so we are familiar with this this problem, this part of the problem. Second part of the problem, that is B, is the flow physically possible? If so, obtain the expression for stream function. This also we had done. So how to get the possibility of a continuous flow? That is, the continuity equation should be satisfied. So what is a continuity equation in 2 dimensions? Dou u by dou x plus dou v by dou y equal to 0. We had determined the equation for dou u by dou x and dou v by dou y in the previous slide. You see this? Dou u by dou x, it is 2 minus 2xy, and dou v by dou y, it is 2xy minus 2. So if you are substituting, you will be getting 0 as dou u by dou x plus dou v by dou y, that is equal to 0. So the flow is physically possible. So if the flow is possible, we can define velocity, potential function, stream function, etc. So how to get the stream function? So this part is very important. This is a typical problem. How to get the stream function if velocity components are given? So we take the total differential of psi, that is d psi. We have derived d psi equal to dou psi by dou x into dx plus dou psi by dou y into dy. That is the total differential of stream function. Dou psi by dou x, as per the definition of stream function, it is minus v dx plus u dy. So psi will be integral minus v dx plus u dy. V and u are known. V is, for example, it is v is 2xy minus 2, and u is v is xy square minus 2y minus x cube, and u is y cube by 3 plus 2x minus x square by. So integral this v dx plus integral u dy. So what is integral minus x square y? Sorry, integral minus xy square with respect to x, you can integrate. So y square and x square by 2. Similarly, integral 2y with respect to x, that is 2xy. So you can complete the different integration part and you will be getting psi as this function, x raised to 4 by 12 plus y raised to 4 by 12 plus 2xy minus x square y square by 2. So you should be thorough and conversant with doing integration. Okay, so that is psi, that is the second part of the problem, that is also completed. Third part of the problem, what is the discharge between the streamlines passing through 1, 3 and 2, 3? We have just done this in the previous problem, that is psi 1 minus psi 2, that is rate of flow between two streamlines, psi 1 and psi 2. What is psi 1? X and y, you have to substitute 1 and 3 respectively. For psi 2, x and y, you have to substitute 2 and 3 respectively. So psi, the value of psi, you substitute x and y accordingly. Psi at 1, 3 will be, if you substitute x equal to 1 and y equal to 3, you will be getting psi is at 1, 3 equal to 8.33 meter per second. Similarly at 2, 3, the value of stream function is 2.089 meter per second. So if you take the absolute value of the difference between the stream functions at 1, 3 and 2, 3, you are getting the discharge as, it is meter cube per second. Discharge between the streamlines, it is 6.25 meter cube per second. So you should correct it, it is meter cube per second, not meter per second. And the fourth part of the problem, that is the flow irrotational? That is, we have to check the irrotationality of the flow. If it is irrotational, that is a potential flow, then we can find out the velocity potential phi. So how to check the irrotationality? Again, it is the flow is happening in the xy plane. We had done a similar problem. The flow is happening in the xy plane. So obviously the rotation vector is along the z direction or z axis. So what is omega z? Either you have to learn this by heart, or you should be able to derive at the time of examination from the easiest technique I had discussed in our theory sessions. So omega z equal to 1 by 2 into dou v by dou x minus dou u by dou y. So dou v by dou x and dou u by dou y we have already found out. You substitute it, you will be getting omega z, the rotation vector component, as 0. So the flow field is irrotational. The flow field is irrotational. You read it as irrotational. Then since it is irrotational, the velocity potential function exists. So this is important. How to arrive at the velocity potential function? We are following the same procedure as we followed for the estimation of stream function. So total differential of velocity potential function, that is d phi, equal to dou phi by dou x into dx plus dou phi by dou y into dy. So as per the definition of potential function, d phi, it is equal to u dx plus v dy. So integrate to get phi. So u and v are known, so integrate with respect to dx plus v with respect to dy, and you can simplify. You will be getting phi equal to x square minus y square plus 2x y cube by 3 minus 2x cube y by 3. So we are getting a similar equation, similar to our stream function. So that is the only thing is, for finding out this functions, stream function as well as velocity potential function, if the velocity components are given, we start with total differential and substitute, and integration you should be thorough. The last part of the problem, show that each of the stream and potential functions, that means stream function and velocity potential function, satisfy the Laplace equation. Okay, so Laplace equation we know. Laplace equation for velocity potential function we had discussed in our theory session. Dou square phi by dou x square plus dou square phi by dou y square, that is a Laplace equation, that is equal to 0. That is a Laplace equation. We should prove that the velocity potential function phi satisfies the Laplace equation. So what is phi? In the previous slide we have arrived at an equation for phi equal to x square minus y square plus 2x y cube by 3 minus 2x cube y by 3. So you differentiate, first differential dou phi by dou x. So you are differentiating the whole equation with respect to x. So differential of x square with respect to x, so 2x, differential of y square with respect to x, that is 0. Then it is differential of 2x y cube by 3 then with respect to x, that is you can also differentiate it as then differential of minus 2x cube y by 3, that is minus 2x cube y by 3 itself, minus 2 by 3y into 3x square by 2. Okay, that is written here. And the third term, differential of 2xy cube by 3, so you take 2y by 3, 2y cube by 3 outside, so you will be getting 2y cube by 3 into differential of x with respect to x is 1 itself. So you simplify, you will be getting 2x plus 2y cube by 3 minus, you can 3 and 3 cancels off here, 2x square y. So then that is dou phi by dou x. You differentiate again, that is second differential, then you will be getting dou square phi by dou x square, that is dou by dou x of this. So 2x, so dou by dou x of 2x is 2. This term does not contain any x term, so differential with respect to x is 0. And this is, you take minus 2y outside into 2x, so you will be getting minus 4xy. So 2 minus 4xy, that is dou square phi by dou x square. Similarly, you can find out dou square phi by dou y square also. Okay, because dou phi by dou y you can find out as minus 2y plus 2xy square minus 2x cube by 3. And differentiating once again with respect to y, you will be getting dou square phi by dou x square is minus 2 plus 4xy. So you add dou square phi by dou x square and dou square phi by dou y square, you will be getting 2 minus 4xy plus minus 2 plus 4xy, that is 0. That means velocity potential function satisfies a Laplace equation. Only thing is, you should know how to differentiate a complex function. So you should be thorough with the integration as well as differentiation in order to do almost all problems corresponding to the kinematics of fluid flow section. Similarly, you can prove that the stream function also satisfies a Laplace equation. That you can do by yourself. Only thing is, dou square psi by dou x square plus dou square psi by dou y square equal to 0 we have to prove. So dou psi by dou x you can find out, dou psi by dou y you can find out. You once again differentiate to get the second order differential. Then you can see that this also satisfies a Laplace equation. That you can work out by yourself. So with this we complete almost all typical problems which were asked for the previous university examinations from the section fluid kinematics. So just to consolidate, we had discussed about the essential characteristics of fluid flow, Eulerian velocities and acceleration, rotationality, then the possible case of fluid flow, the condition for the flow to happen, continuity equation we had discussed, then the most important flow net of a fluid flow. So that is an orthogonal combination of streamlines and potential lines. Then we discussed about the stream tube, that is actually mimicking a tube with entry at one end and exit at the other end. And also for clarity in understanding, we had seen various flow patterns which are nothing but the flow net representations. Okay, then after this we will discuss about the fluid dynamics in the coming video sessions. Thank you.